We want to build an artificial kidney, and we know that breaking that down into the individual components, it needs to recapitulate the normal function that the kidney does in the body, which is that the kidney filters blood by connecting to the blood supply, and each kidney is then packed full with the million individual nephrons, which are long tubes that are specialized in nutrient reabsorption and controlling water balance. And at the other end of this tube, it connects to a common drainage system. And this is critical because you need to lead urine out into the bladder. But when we're generating an artificial kidney, does it really have to look the way that the kidneys do in our body, two individual blocks of kidneys that do all the function? Well, I think that what nature has told us is that there are many solutions to a problem. And if we turn to the solution of fin whales and these extremely large mammals, they have had to figure out a new solution to the scalability of becoming extremely large but still needing to efficiently filter their blood. And if you look at their kidneys, actually they look almost like a bunch of grapes. Each grape is an individual kidney that's connected to the common blood supply, and it's also connected to a much larger intricate network of a drainage system that can then lead urine out. So the KidneyX initiative has told us to think bold, think bigger, think better. And I think that's exactly what we're trying to do here. My lab, we are experts in the development of the kidney. We start with human stem cells. We then coax these stem cells to begin to differentiate like they would do in normal development. And they form nephron-like cells. And we generate thin discs of these, where each disc, approximately the size of a pea, consists of about 400 to 500 individual nephrons. So if you think about that as a problem of scalability, if you have just 1,000 of these little small pea-like artificial kidneys, and you would then have 400,000 individual nephrons, which is approximately half of one of your kidneys. So then looking at the problem of how are we going to make each of these small pea-sized artificial kidneys connect to the blood supply at one end and to the drainage system at the other end, we reached out to Leonardo Morsut's lab.
What we do specifically in our lab is controlling with artificial circuits cell behaviors when the cells are trying to build organs and build tissues, so that we can control things like the patterning, the organization of how the cells are organized in space, so that we can build something that ultimately wants to be something that has a coherent function of the whole assemblage of cells. And when we're talking about function for the kidney, what we're focusing on is creating a continuum that goes from the blood that needs to be filtrated into urine, so that the fluid can have a continuous, almost like tubing system to get from one end to the other. And in particular, with our synthetic cells, we're helping the nephron recognize that they need to connect to a drainage system, which they don't do if they don't have any organizing principle from the outside.
And this is exactly the solution that you see in whales. So we think this is a great scalable and modular solution to how we're going to build an artificial kidney that actually can restore renal function.